All right, this video will be a little shorter just because we don't really have any new linear algebra theory, but we'll be applying what we've developed so far to some applications. So this first one, we have 3 points, 2, 4, 3, 6, and 6, 12, that we're trying to fit a polynomial to. And we want to fit the least degree polynomials to those given points. So if we have 2 points, we would need a line to fit those 2 points. If we have 3 points, we expect a quadratic. So I'll write down our general quadratic equation, this parabola. And we don't know what a, b, and c are yet. Those are unknown. If we did know a, b, and c, then that'd be our solution. And we'd know the parabola that fits these 3 points. But we're trying to figure those out. What we can do is plug in our x-coordinates and our y-coordinates into that equation. And we find out we have 3 equations and 3 unknowns, the unknowns of a, b, and c. We can write this as an augmented matrix. And then apply row operations, those mathematical moves that transforms this into reduced echelon form so that we can read off our solution. So if you do those row operations, you'd eventually get to this reduced echelon form. And so therefore, a is equal to 0, b is equal to 2, and c is also equal to 0. So that's our solution. And this means actually only a line is needed to fit those 3 data points because a is 0. So b is equal to 2 and c is equal to 0. So the polynomial is 2x, right? We didn't actually need a parabola. We found out a is just 0. And you can plot those points and the line 2x and realize that 2x does cover all 3 points here. Right? You could even just plug in x is equal to 2, 3, and 6 and realize you do get 4, 6, and 12. All right. This next problem, we have 4 points that we're trying to fit a polynomial to, so we'd expect we need a cubic function this time. So here's our general cubic function, and we can plug in our x and y coordinates in again to get 4 equations and 4 unknowns. And write our augmented matrix. And I'll let you complete this homework problem on your own this time. Right? Just get this in reduced echelon form to figure out what a, b, c, and d are. And that would solve the problem. Now this problem, we're looking at the flow of traffic for this network of streets. And the number shown is the number of cars per hour, the number of vehicles per hour. So like in the top left intersection, there's 400 vehicles entering that intersection per hour on the left-hand side, but we don't know how many vehicles are entering from the south, that is x2, and how many are exiting the intersection, that'd be x1. So we don't know what those are yet. x1 and x2 are unknown. And we also have 3 other unknowns, right? x4, x3, and x5. We don't know what those are yet. But we could set up a system of equations. We could develop an equation for each intersection here. And the way we will develop those equations is we realize that the number of cars going into the intersection needs to be the same as the number of cars going out, right? The in needs to equal the out traffic. If the in wasn't the same as the out, maybe if the in was more than the out, that means you have like vehicles building up at that intersection, which doesn't really make sense unless there's a car pile up. And if you have more cars going out of the intersection than going in, then that doesn't really make sense. It's like cars are being created inside of the intersection. So that doesn't really make sense. So the amount of cars going in and out need to be the same. So for that top left intersection, we can say 400 plus x2 is equal to x1, right? That's in is equal to out. The left side is the amount of traffic going in, and the right side is the amount going out. Top right equation, we know x1 plus x3, that is the traffic going in, needs to equal the traffic going out. That's 600 plus x4. The bottom left intersection, 300 is the only traffic going in, and so the rest are going out. That is x2, 3, and x5. And the bottom right intersection, x4 and x5 are both traffics going into the intersection, and 100 is going out. So the in needs to equal the out. So now we have 4 different equations for those 4 intersections, and we have 5 unknowns. Now what you could do is set up the augmented matrix. and apply those mathematical moves to get into reduced echelon form. And I have that shown here. And then we can describe our solution. Right? The top row is saying x1 is equal to 700 minus x3 minus x5. Second row is saying x2 is equal to 300 minus x3 minus x5. And x4 is just equal to 100 minus x5. All right. So if the system has an infinite number of solutions, we're going to express x1, x2, x3, x4, x5, that is all the traffic, in terms of parameters s and t. So we've only been able to solve for x1, x2, and x4. So that means x3 and x5 can be anything. And whatever you choose for x3 and x5, that will determine what x1, x2, and x4 are. Right? So what you can do is let x3 be equal to s, so this parameter s, and you can let x5 be equal to t. Right? And then you can describe all x1, x2, x3, x4, x5 in terms of s and t. Notice in part B and part C, they actually give us numbers for the traffic for x3 and x5. And so that means you have values for s and t. And that means you can figure out what actually x1, x2, x3, x4, x5 are as a single solution. But in its current form right now, what I have written down, there's an infinite number of solutions to this system of equations. So you need a little bit more information, like in part B. If you knew x3 is 0 and x5 is 70, then you could get one single solution for that system if you knew that x3 is 0 and x5 is 70. All right, I'll leave it at that. That's it for the video. Thank you.